Hey everyone, welcome to Notes 2.03. This notes is going to be pretty quick today on dilations and a new word for us, isometry. So getting started. A dilation is a similarity transformation, not a rigid motion. So we are going to briefly talk about dilations, but really for the most part for this unit, we need to know that it's not one of our rigid motions. A notation for dilation is a capital D, and there might be a little letter here like O, comma 2. What that means is you dilate with the center at the origin, and a dilation of 2 means twice as large. So looking at the little sketch here, we have to decide, is this shape getting bigger or smaller? So remember to look at the notation. The capital A is here. This one is A prime. So it's getting closer to the center of dilation. So this letter O is our center of dilation. That means A to A prime is halfway the distance from A to the center. Same thing with B and B prime. B prime is half the distance in, and this line connecting C to C prime, it's half the distance in. So we could say here that there was a dilation of a half centered at the origin. So it's getting half as big. That the length of AC, if this was, let's say, 18 units long, A prime, C prime would be 9 units long, where its length became half as well. The scale factor is this number right here. So 2 would mean twice as large. So scale factor is the number you would multiply by. So if it's 2, it's twice as big. If it was 3, it would be 3 times as large. Okay. Exercise 1, dilate the following points. O is the origin. So if we had the point 5, 3, that means it's 5 to the right and 3 up. And our dilation rule says dilate around the origin 3 times bigger. So guess what we're going to do? We're going to multiply each part of the ordered pair times 3. So 5 times 3 gets us 15. 3 times 3 would get us 9. So we take each ordered pair and we multiply it by a scale factor. Dilation here says of a third. So dilation around the origin of a third means 9 times a third and negative 6 times a third. So if I grab my calculator quickly, 9 times 1/3, or a third of 9 is 3. And I know a third of negative 6 should give us a negative 2. So we're just going to multiply by a third, or really divide through by a 3 there. So again, that should be a 2. Sorry about that. 3/4. So 3/4 is our scale factor. So again, that multiply, that's the number we multiply by. That's called also the scale factor. So negative 4 times negative 3/4 gets us a positive 3. Denominators cancel there. And 12 times negative 3/4 gets us a negative 9 as the y value. Okay, so we just multiply through. 2.5 is our scale factor here, 2.5 or 2.5 times bigger. So 10 times 2.5 would be 25. Negative 6 times 2.5 is still negative, but it'd be 6 times 2.5 is 15. I'm going to say 18. It's been a long day here in the building. All right. So again, scale factor, we just multiply is that key word. Okay. Isometry is considered a rigid motion. Those words mean the same thing. I'm just trying to change color. So an isometry is just a fancier way to say rigid motion. It preserves length of sides and angle measures. Again, you've heard me say that definition a few times now. It was at the beginning of our packet and here on the notes page. But an isometry preserves the distance. between the points. So like the tentacles of this little octopus guy, the distance between one tentacle to another is going to be the same after a reflection, after I rotate him around some center of dilation, or if I translate him, he stays the same size and the angle of each of his little tentacles stays the same. A dilation, so maybe we dilated 5 times bigger here. Okay, from here he got 1, 2, 3, 4, 5 times bigger. That is not an isometry. So again, that's another vocabulary word that just means rigid motion. So isometry is another word for rigid motion. We can go farther to talk about a type of isometry. So we can have what's called a direct isometry or an opposite isometry. Trying to get my camera situated, sorry. A direct isometry is when the points, meaning the vertices A, B, and C, go in the same direction. So notice here, we're going to talk again clockwise, CW, and counterclockwise. I'm going to be describing right now. These ordered pairs, A, B, C, as I go around that shape in alphabetical order, A to B to C, those ordered pairs go in a counterclockwise orientation. And if I translate that image, that didn't change. A prime, B prime, C prime, still go in a clockwise orientation. So that's called a direct isometry. The points go in the same direction. Same thing with a rotation. If my triangle started here and then I rotated it to here, okay, D, E, F, and if I label D prime, E prime, F prime with a clockwise rotation, okay, look at the ordered pairs. D to E to F around my shape goes in a clockwise fashion. Even after the rotation, D prime, E prime, F prime still are going around to our right. So that's considered a direct isometry. An opposite isometry, or another word for opposite would be indirect, means not in the same direction. So a line reflection, D to E to F, those ordered pairs go around to our right. Okay. But if you flip that shape over, so again, DEF is to my left and it flips over my line of reflection, okay, where F stays closer, E gets farther, and D moves farther. Okay. That orientation changes. To go from alphabetically D prime, E prime, F prime, it goes in reverse order. So this is called an opposite isometry. Now, if I were to reflect that shape again over a new line, E double prime, D double prime, F double prime, the first to the third would stay the same. So double line reflections end up being a direct isometry, but that's just a little bit of extra vocab that might come up in a multiple choice question or two. This topic, again, is not on the quiz that you have in class this week, so don't stress too much there. On to the back. Here are 4 questions deciding if it's an isometry or not. So tell whether each is an isometry, yes or no. And if it is an isometry, tell us if it's direct or opposite. So are the points going the same way or not? So I'm going to do 1 and 2. I'd like you to try on your own 3 and 4. So I'll be looking for that when you submit your work shown, or I see you in class next. But for number 1, this shape is a reflection, so a reflection is an isometry. So I'm going to say yes. Okay. A reflection is a rigid motion. And looking at the ordered pairs, A, B, C, D for the first picture goes to the right. So that's a clockwise orientation of the letters. A, B, C, D goes around our shape to the right. A prime, B prime, C prime, D prime goes around to the left. That would be an opposite isometry. From one picture to another here for number 2, okay? That's not a translation, it's not a slide. And I have this wax paper here I'm gonna trace over to just show us that. I like to line it up to a corner as I go to trace these. So this tracing paper, I can give you some, or if you have wax paper at your house, you just use the non-waxy side. To decide what kind of transformation is happening, I can move this up, down, left, right, and see that it's not a translation. There's no way I can format what I started with onto the new shape. So what this is actually going to be, it's going to be more of a rotation. Okay. Now I think I have to rotate a little bit more to get those points to line up a little bit better. So again, going back here, if this is A and this is C, how do we get A and C on top of another? If I rotate it maybe clockwise around, there we go. A falls to A and C falls to C. So this tracing paper can sometimes help you identify what kind of transformations are happening. That's what we're going to be doing over the next few classes, as identifying our transformations. So this is a rotation. So yes, it is an isometry because a rotation is a rigid motion. And the ordering of the points, A, B, C goes around to the left. A prime, B prime, C prime, these arrows I'm drawing is a way to decide if it's direct or opposite. Both arrows are going in the same direction, so that's a direct isometry. So I'd like you to try 3 and 4. A hint there is one of them is not an isometry, so you don't need to tell me if it's direct or not. Looking at exercise 5. Again, over the next few classes, we have to make decisions on how does one shape fall on top of the other. And I know some of you have been doing really well with that in class, and some of you need a little assistance. So if I trace over the shape again on my tracing paper, W, S, P, the last letter I, oops, okay. We have to decide how does this shape move to fall on top of the new one. So again, sorry, my finger's kind of in the way here. I'm just trying to keep the paper down toward the tracing paper flush against the regular paper. But that shape, we kind of shift over a few boxes and down a couple boxes. You can kind of see the ghost shadow as it's moving. Ooh, down and over. I'm sorry, over and down. So it's moving to the right 1, 2, 3 boxes, and then it moves down 1, 2 boxes, and everything falls on top of itself. So list a rule for the transformation. You can do this 2 ways. So again, it moved to the right 3 and down 2. So you can say translate right 3, down 2. Or to write the rule, it translates 3 in the x direction and -2 in the y direction because it goes down. Okay, so you can write it out in words or you can list it as the rule. Some of you have preferred that x comma y, the x add 3, y subtract 2. Again, this and this mean the same thing. Okay, so depending on how you want to write it is fine with me. Is this a direct or opposite isometry and why? Well, this is going to be a direct isometry because W and S fall top to bottom for each other. So this is going to be direct isometry. I'm actually going to skip the Y for today. Okay, number 6. Points A, 0, 2, B, -4, 0, and C, 3, 4 are plotted below. Find and plot their image after a dilation of scale factor 2, centered at the origin. So A is 2 away, C is a bunch of boxes away, and B. So if we kind of make a little straight line there and a triangle back to our center of dilation, what we're going to do with each of those ordered pairs is when we dilate by 2, we multiply by 2. So A prime is going to become 0, 4. So it got 4 boxes. It got double the distance. B prime would become -8, 0. And C prime, if it's 3 away in the x direction, it's going to become 6 away, and 4 becomes 8. So graphing the new diagram, A jumped 2 boxes more up to become A prime. C goes 2, 4, 5, 6 over 8 up. C prime. So its distance became doubled. So that's one length out, and it became another length out. So double the distance from our origin. And B is to the left 8, up 0. So those 3 points kind of stayed in a nice little line there, but they became twice as far. How can you verify that C prime is twice the distance as its original point C? Well, we have a distance formula, don't we? Okay. We could calculate how far C is over to the origin, kind of using our Pythagorean theorem. So C prime to the origin, so again, C prime's way up here, that is 8 boxes over, and I'm sorry, 6 boxes over, my mistake, and 8 boxes up. So the distance from O to C prime is 6 squared plus 8 squared equals our C squared, that hypotenuse, the whole length from O to C. So 6 squared and 8 squared is 36, and 64 adds to 100 is C squared. So that distance is 10 units out. Okay. If we were to find point C to the origin, too many O's, C to the origin, now that point's only over 3 and up 4. So over 3 boxes and up 4 boxes to find its length away is 3 squared plus 4 squared equals C squared. Gives us 9, and 16 adds to 25 is C squared. And again, remember we need the square root there, is 5 units away. So the distance did get twice as large. So that's just a little bit about scale factors. Again, we're going to come back to this in another unit about similarity, because really we just drew 2 triangles that are proportional to each other. 3 compares to 6 as 4 compares to 8. So we're going to be writing proportions, like A is to B as C is to D. So that's another unit later this school year. Moving on to your classwork for today, classwork 2.03. What I want you doing for the first question is describing a rigid motion. So how does triangle A fall and become triangle F? Okay, there's actually 2 things it could do. So see what you can understand about that. There's a couple different answers you could give me here, but I want you to describe some kind of transformation to get you from A to F in one single transformation. So not 2 different things. Part B, list a single transformation that gets us from triangle A to triangle G. And again, if I take this tracing paper, I can almost give you a hint for the first one. Okay, I'm going to line it up right there at the origin. And if I trace over triangle A, very carefully here, you can tell I'm taking my time. Okay, and I rotate around the origin, that triangle falls beautifully onto point F over here. But I could also take my paper, I don't know if you notice what I'm doing, I'm flipping it over. Now did that fall on top of itself? So if we do a flip, which would be a reflection, did that triangle there flip and become that triangle there? So there's a transformation to land us from here to there. So see what you can try for number 1. Letter C says, is A congruent to F? Well, I traced over A to begin with, and does it land perfectly on F? Yes, it does. So that answer here, I'm going to tell you, is a yes. Okay. The second section here, tell which transformation each pair of figures simulates. So I want to know, is this a reflection, rotation, translation? What's happening here, here, and here? If it's a series of 2 different things, let me know, but I just want to know if you can identify and how you can identify. Number 6, I do want to explain quickly. Identify the rigid motion used moving the pentagon from the first position to the second. So I'm going to, again, sketch this for us. If I trace over that first pentagon, it has a side of 9 and a side of 2x plus 1, because we have to solve for x and y here. What we need to do is we need to take that pentagon, and they kind of show you a little arrow here around point P. If I hold down the corner of my paper at point P and I start doing this, that shape rotated. So when it says to identify a rigid motion, there's a rotation. And how many degrees is that rotation? So we've been doing 90 degrees or 180. In this case, it's a rotation of 180, 128. So how we're going to write that is a rotation. In what direction did it go? It went to the left, so it went counterclockwise, 128 degrees around point P. That is a nice specific explanation of what happened, right? So we have to get to a place that we can narrate that. Now to solve for x and y, well, rotations preserve length and angle measure. So what that means is that this side of the 2x plus 1 from the original and this side, the 6x minus 19, are the same measure. Those lengths are equal. So you're going to set 2x plus 1 equal to 6x minus 19, and the same thing with the 9 and the 3y. So we'd like you to solve for x and y here to continue out. The back should be pretty self-explanatory. Number 7 is kind of the same idea. Identify a rigid motion that moved you from one to the other, and just a simple word could help. 8, same case. And with this one, be careful. You're moving from ABC to DEF. I want you to explain how you're moving from this triangle up to a ghost over to this triangle. So see how specific you can get here with number 8. And 9 and 10 are some nice multiple choice questions. Good luck. We appreciate it. See you guys soon.